Hi, my name is Ross Dixon. This is the ACENET Basics Seminar, Job Scheduling with Slurm. The job scheduler is a piece of software on a high-performance computing cluster that decides what calculation to run next and where to run it. The job scheduler that we are currently using on Compute Canada equipment is called Slurm. The scheduler accepts a description of the work to be done, just the name of the program you want to run, what input file you want to run it on, optionally where to put the output, and a few other specifications that go with scheduling a job, such as how long it's allowed to run with the time parameter, and perhaps an account parameter. You bundle all this information into a file. I've called this one simplejob.sh, but you can call it anything you like. And then you use the sbatch command to submit the job to the scheduler, sbatch simplejob.sh. And if the scheduler accepts it, it gives you a response. On Compute Canada systems, it's essential that every job be associated with some allocation. And to do that, we use the -- account parameter. Now, it's possible that your login is only associated with one allocation, in which case you don't need to worry about this, and when you submit a job, you won't see this stuff. But if you see the error messages that I've got showing on the screen here right now, simply just read the error message. It pretty much explains what's wrong and what you have to do about it. It says you are associated with multiple CPU allocations. Please specify one of the following accounts to submit this job, and then it lists accounts. They may have names like def some PI's name, def some PI's name with letters after it, RRG, RPP. There are various possibilities. Use the parameter -- account equals desired account when submitting your job. So just do what it says. Put -- account equals one of these things in, and your job should run okay. So, as I said a few seconds ago, you use the sbatch command to submit the job. You can optionally provide parameters as additional arguments to the sbatch at the command line, or you can supply them on the inside of the script with the #sbatch prefix on them. Doesn't matter. If you've got both there, the one you provide on the command line will take precedence. You can use either, but we generally assume that you're going to put them inside the script, and the rest of the talk will assume that as well. When you type sbatch, name of some job script, if your job's accepted, it says submitted batch job, and it gives you some number, 1, 2, 3, 4, 5, 6. That's a sequence number. On each cluster, jobs are given new numbers in strict order. That means that every job that's accepted by the system has a unique job ID number. And that's useful later when it comes to troubleshooting. So I just want you to remember that you saw that first here now. When you type sbatch, you get the job ID number. After you've submitted the job with sbatch, you can check how it's doing with the squeue command, squeue. On Slurm, you should provide your username -u, your username, or $user, which will do the same thing. Because otherwise, squeue will tell you about all the jobs in the system, which is probably more information than you want. So to inquire about just your jobs, squeue -u, your username. And it will tell you the list of all the jobs that you have in the system. There's the job ID numbers again. The job has a name that may correspond to the name of the script you gave it, although there are ways to change that. The fields that you're probably most interested in is this column labeled ST. If the ST column describes the state of the job, or the status. If there's an R in the ST column, that means it's running, and so you'll probably see a start time beside that, and maybe a list of nodes on which the job is running. If your job hasn't started yet, you'll usually see PD for pending in the status column. And typically no start time, although Slurm may try to predict one. It's not usually very reliable. And over here, it may give some reason why it hasn't scheduled yet, like priority or resources. We'll talk a little bit about those later. If squeue doesn't show you anything at all, just headers and no list of jobs, and that means you don't have any jobs in the system anymore. Probably your jobs have already run. That's in line with the usual Unix practice. No news is good news. By policy, every job that's submitted on Compute Canada's system has to have a time parameter supplied. We do not provide a default runtime for your job. The time parameter is a time limit. It is a hard time limit. That is to say, after a job is started, when it starts computing, then after that time limit has expired, the job will be killed. The idea here is we don't want jobs that go into that get hung and never finish, and we don't want jobs to get into weird infinite loops or anything. It's also very useful for the scheduler to have an idea of how long a job is going to take. It allows the scheduler to schedule things more efficiently. But because it's so accurate time limits are useful to the scheduler, but because it is a hard limit and your job will be killed, it's important that you leave a margin for error. Runtimes on clusters are not perfectly predictable, especially if the job is doing a lot of input-output. The response time of the file system may be variable, so leave yourself a margin for error. 10 or 20% is not a bad idea. Possibly more is okay. And you can specify the time in a number of forms. If you just put in a number, it'll be interpreted as minutes. If you put in a colon, it's minutes and seconds, otherwise hours, minutes, seconds. And if you can provide days, dash, hours, minutes, seconds if you like. Another resource that you can optionally ask for is CPU cores. There's a lot of parallel computing that happens on high-performance computing clusters. One could argue that's pretty much what they're designed for. And so if you're going to be running any sort of parallel program, then you need to know how to ask for the number of cores that your program should run on. In order to do this, you need to know a little bit about the nature of the program you want to run. You need to know whether it is a distributed memory program that uses MPI, for example, or whether it's a shared memory program that uses OpenMP, for example. Threads also fall into the category of shared memory. And it's also possible to ask for CPUs that work for hybrid jobs that are both distributed and shared, but I won't describe that in this talk. If you're doing distributed memory processes like MPI, then you should use N tasks. If you're doing shared memory, you should use CPUs per task. There's documentation about many of these things at docs.computecanada.ca, and you can look for running jobs is the key page for all of the things that I'm going to be talking about in this session. So an example script for an MPI job would include the line #sbatch --n tasks equals 4, and that will start 4 MPI processes. MPI programs, if you're familiar with them, you may be familiar with the idea that you start an MPI program with MPI run or MPI exec. With Slurm, we prefer to use srun. These others will work, but srun is better integrated with Slurm. It'll give us better job monitoring and statistics, and should otherwise work just as well or better than MPI run or MPI exec. You probably won't notice the difference. Mostly it's us that notices, but we'd like you to use srun instead of MPI run for MPI jobs. For OpenMP jobs, the advice I gave you is to use CPUs per task. With OpenMP programs in particular, OpenMP generally gets the number of lightweight processes, the number of threads it should use, from an environment variable called OMP num threads. Slurm does not automatically set OMP num threads, but Slurm will provide you with another variable called Slurm CPUs per task, which you can copy into OMP num threads and set the OpenMP thread count that way. Now, if you're going to be running particularly large parallel jobs, and this will usually mean distributed memory or hybrid distributed shared memory, then it may be advantageous to you and to us as well if you ask for complete nodes to run your job on. If you simply use the n tasks shown on this slide and you ask for 128 tasks, for example, those 128 tasks, processes, could be started on any number of nodes from a minimal number 4 all the way up to 128 distinct nodes. If it starts on 128 distinct nodes, that's bad for the performance of your program, and it's bad for the future performance of the scheduler as well. So if you're running large numbers of processes, where large is arbitrarily defined as something well north of 32 cores, and you can use more than 32 cores efficiently and in numbers divisible by 32, then it's best to ask for complete nodes. And there's new commands for that. You should use the -- nodes parameter to ask for the number of nodes, and then a number of tasks per node. Typically, the number of tasks per node will be 32 because the vast majority of our equipment in the general purpose clusters Cedar and Graham have 32 cores per node. So you ask for a whole node, you ask for 32 cores per node with n tasks per node, and 1 CPU per task. There are a growing list of exceptions to this, however. The nodes at Cedar equipped with GPUs have 24 CPU cores. There are a new batch of nodes have been installed at Cedar in recent months that have Skylake processors in them and 48 cores per node. The extra large memory 3 terabyte nodes at Graham have 64 cores per node. And the nodes at the new Niagara large parallel cluster have 40 cores per node, hyper-threaded up to 80. So the rule of thumb is 32 cores per node, but there are a lot of exceptions. For help straightening this out, go look at docs.computecanada.ca again. Advanced MPI Scheduling is a good page, and the advice there may evolve over the coming months. Another resource that you may wish to ask for is memory. By default, if you don't ask for any memory, your job will be assigned 256 megabytes per core. That's not an awful lot. It's good for some processes, but there's probably a lot of calculations that need more than that. And so you simply request more. You can ask for more memory per CPU, or you can ask for the memory per node, which goes particularly well with whole node requests, as I just described. Both of these, mem or mem per CPU, are hard limits, much like the time limit. If the job tries to use more memory than that, the job will be killed. Why do we do this? You don't normally have to worry about memory if you're just running stuff on your laptop or your desk-side machine, do you? Well, there's a number of reasons. The main one is that many of the compute nodes here are shared with other users. So you're not the only person using it, and if something goes wrong, then you're affecting other users. What could go wrong? Well, it turns out that if your job and the other user's jobs combined exhaust all the RAM on the machine, then the machine may start using swap and performance may drop by as much as 2 orders of magnitude. Or one or the other of your jobs will simply be killed because the operating system needs to keep things going, and if it's out of memory, it can't. The amount of memory available is different on different kinds of hosts we have on our machines currently available. The basic and most common node design at Graham and at Cedar has 128 gigabytes. You should probably treat that as 127,000 or 128,000 megabytes. Difference between 1,000 and 1,024 gives us just enough room for a little bit of memory needed to keep the machine running, a little bit of memory for the operating system. Another resource that some of you may be interested in are GPUs, or graphics processing units, or general purpose graphical processing units, GPGPUs. There are only a limited number of machines at both Cedar and Graham with GPUs. There are none at Niagara. So in order to request one, you need to insert this line in your job script, --gress equals GPU:1 or :2. GRES stands for generic resource, and this tells it how many GPUs to request. If you want to know how many GPUs are available, you can look this up at docs.computecanada.ca as well. I'll just sketch it here. At Graham, the GPU nodes have 2 GPUs, so the largest you can ask for is GPU:2. At Cedar, there are 4 GPUs per node, so you could go up to GPU:4. And remember, as I mentioned earlier, there are 24 CPU cores on those nodes. Again, look up the details on the documentation site. There's a page on using GPUs with Slurm that will help you out here. By default, when you submit a job script and the job runs, Slurm will put the output in a file called slurm-1234556, whatever the job ID number was, .out. This has certain advantages, the major advantage being that the output is captured in a file that contains the job ID number. And so if it comes around that that job didn't do what you expect, and you want to write to support and say, why did job 123456 not give me the output I expected? The job ID number is right there in the file. You don't need to write it down separately in another file or your lab notebook, or forget about it. And when you write us, you can just quote the job ID number just by reading it off the output file name. However, a lot of people find that slurm-sumnumber.out could be better for their purposes. You may have different classes of jobs, and not having all their output called slurm-something is not what you like. So you can change this. First of all, you can change the job name that will show up in the SQ output just by setting job name equals something. That will also change the name of the output file because, no, sorry, it will not change the name of the output file, my mistake. You can then change the name of the output file if you like, using this line in sbatch. %x and %j are some meta characters that Slurm defines for its directives. %x is replaced by the job name, whatever you set up here with this command, and %j is replaced by the job ID, which is part of the default. I encourage you to keep it, although you're not obliged to, of course. So if you've submitted your jobs and they're waiting and you realize, oh, something's gone wrong, I want to change what I've asked for, or I don't need to run this job at all, or whatever, you can simply cancel it with scancel and the job ID number. There's that job ID again. You can cancel all the jobs belonging to you if you want with scancel-u and your username. Or you can do things like cancel only the jobs that are in pending state belonging to you, for example. Don't worry, you can't cancel other people's jobs by putting in their username. You don't have that much privilege. What if you just want to change something about the job? You realize that you should have asked for more memory or less memory or a different number of CPUs or something. The simplest thing to do is simply cancel the job and then resubmit it. Because of the way priority works, that has a minimal effect on your position in the waiting list for when your job will run. There are ways to alter jobs without canceling and resubmitting them, but I'm not going to get into them in this talk. So with those commands, sbatch, squeue, scancel, you really have the 3 things that you need to actually be productive on a Compute Canada general purpose system or a large parallel system. You know how to submit jobs, you know where the output's going to go, you know how to request resources. The rest of the talk is essentially going to be about troubleshooting. What sort of things go wrong with job schedulers? Well, there are 3 major classes of things that go wrong. I'm going to handle them in order. First one is your job's submitted, it's accepted, it runs, it crashes, or you get no output or truncated output or something like that. The second type of problem is the jobs are fused. You type sbatch job script and it says error, batch job submission failed. It doesn't give you a job ID. The job has not gone into the system. Third class of problem is the job's gone in, but it hasn't run. And it still hasn't run, and it still hasn't run, and it's waiting a long time, and you want to know why. So let's tackle these three in this order. Job crashes. What's going on? 19 times out of 20, if your job is crashed, it has to do with the code you're running. So how do you figure that out? Well, first of all, before I even get to what's written on this slide, have you tried running a really small test program on the login node? You should find a test case that'll only take at most 5 minutes, and just make sure that the program actually starts and doesn't crash right out of the gate running at the command line. If you can do that, then maybe you might have to start thinking about what Slurm is doing to it, independent of what's going on. And you can do that with a small test run with srun. Srun, some short time limit, 3 hours at the most, but 5 minutes is a better idea. Run the code, take the input from whatever. That tries to get immediate service for your job. If the resources simply aren't available, it'll simply turn you down. It won't queue something up to wait for later. Look at all the output that you get. Don't forget to look in slurm-something or other.out file. Look at whatever output files you redirected things to in your job script. Look at any files that the program just arbitrarily writes. Make sure there aren't some error messages in there somewhere that you've missed. But srun for an interactive session is one option. There's another option for an interactive session as well. Salloc. Some people pronounce that salloc, but I think it's best to think of it as slurm allocate. Salloc, ask for a time limit, ask for some number of CPUs and memory if you like, supply an account if you need to. Salloc will give you an interactive prompt. It'll give you a bash prompt. And you can just go on as if you were working at the login node, except that you're now working on a compute node and you've got a little bit of Slurm context in. Srun just tries to run some command directly. And in any case, 3 hours is the most runtime you can ask for either of these sort of interactive jobs, either a shell prompt with salloc or just running a command with srun. Another common thing that comes up in the context of scheduler, Slurm or any other scheduler where memory is constrained, is that maybe you didn't ask for enough memory. Generally, Slurm is pretty good with its error messages. If the output file says job 1, 2, 3, 4, 5 exceeded memory limit, that's a good indication that you should have asked for more memory. Exceeded step memory limit at some point. Another error that we have seen is you may see detected one kill event in step whatever. This is also referring to a memory problem. OOM is the out of memory killer. It's a little process that runs on most Linux systems and manages the problems that happen if all the programs on board run out of memory at the same time. So exceeded memory limit, that's a good indication. You should try it again, asking for more memory. If you see the kill message, maybe you should also try it again, asking for more memory. But it is also possible to get one or the other of these messages while your job still succeeded. The killer might actually manage to preserve enough memory that your job succeeded. So before you get all panicky when you see one of these messages, check to make sure that your output is actually truncated or missing. It's possible, just possible, that your job actually succeeded despite dropping one of these error messages. Next type of problem, your job's rejected. There is a limit, for example, on the amount of time you can ask for. It's 28 days on Graham and Cedar. It's shorter on Niagara, and it's going to be different on other clusters with other scheduling policies. If you ask for more than 28 days of runtime, then you're going to see a message like error, batch job submission failed, requested time limit is invalid, missing or exceeds some limit. You can get a similar problem if you ask for more memory than exists on any of our machines. For example, if you ask for the biggest machine that we currently have available at Cedar and Graham is a 3 terabyte host. If you use -- memory equals 4 terabytes, you will get a message like memory specification cannot be satisfied. Or requested node configuration is not available. Again, those are fairly self-explanatory, but it's also possible to get messages of this nature even though you're under the time limit and you're inside the memory limit. But we've got policies in place about combinations of time and memory that you're allowed to run on, and I'll talk more about those later in the talk. If you can't figure out why you got one of these messages, feel free to just paste the job script, or at least the sbatch requests, into a note and send it to support@computecanada.ca, and one of the experts will look at it and try and tell you which limit you're exceeding and suggest how you might be able to do the work, what you should rearrange, scale back. So the third and wickedest class of problem that jobs suffer when they're submitted to schedulers is waiting too long. My job won't start. This poor user called user has submitted this job months ago and it hasn't started. Why has it been waiting so long? This is a hard question. It's going to have a slightly different answer for every situation. There's lots of details that go into this. And in order to address this question, I'm going to have to first explain to you a little bit about how jobs are scheduled. How does the system decide which job is going to run next? The basic scheduling algorithm is, first, once a job has been started, we generally don't interrupt it. There's very few exceptions to this. It's just wasteful to start a job and then stop it and restart it, and sometimes it breaks the code you're running. So we don't do that. We pick a job, we start it, we let it run until it finishes, or it times out, or it crashes. Second rule, each waiting job is assigned a priority. I'm going to talk a little bit more at the end about how priorities are assigned, but for right now, let's just take it as read that everybody gets a priority, and in an ideal world, the priorities are about the same. When resources come free, when some job finishes, then what the scheduler does is it looks at the jobs in order of priority, takes the highest priority job and says, do I have enough hardware, enough CPUs, enough memory, enough time, enough GPUs to run this highest priority job? If the answer is yes, it starts it. And then it looks at the next job in the list and says, okay, have I still got enough resources left over to run this job? If it does, it starts it. If it doesn't stop. What it does is it then goes on down the list further until it finds a job that it can run with the resources available, or until it's checked all the jobs, or until all the resources are committed. So just because a job has highest priority doesn't mean it's going to run next. If the job with highest priority is asking for massive amounts of resources, it may take some time before those resources are available. Or if it's asking for a very specific and rare kind of resource, like a 3 terabyte node, for example, it may take some time before that particular resource becomes available. The scheduler is not going to leave other things idle while it waits for that first customer in line to be served. It's going to go on down the line and try and figure out what else it can do to keep the system busy and keep the throughput high. Now, not all resources can take all jobs. As I said, 3 terabytes of RAM, there's only a few resources that will take that. But there are further restrictions besides just the available hardware as well. These are policy restrictions, largely based on runtime. By policy, we will allow on Cedar and Graham jobs of up to a month, but we really don't want the system to become dominated by jobs that are running several weeks. We really want to keep the turnover in these systems very short, down in the measured in hours, hopefully. And so by policy, we have partitions set up that'll take jobs of certain runtimes. So a partition is a group of hosts, a group of machines in the cluster, Each partition has some time limit assigned to it. And if a job's requested runtime is less than the partition time limit, then the job qualifies for that partition. A partition is not exclusive with all the others. Partitions can overlap, or one partition can be contained inside another partition. Besides just the time dimension, we also partition nodes in the two general purpose clusters, Cedar and Graham, based on whether the nodes will accept only whole node work, we call that by-node partitions, or whether they'll accept jobs that take less than a node. We call these by-core partitions. Of course, we also have nodes that only have CPUs, and then we have some nodes that have GPUs as well, so that's another partition. And then finally, there are nodes with varying amounts of RAM on board. Most of them have 128 gigabytes, another chunk of them have 256 gigabytes, and then there are a few with more, 500 gigabytes and 3 terabytes. So the ones with up to 256, we call those the base nodes. The larger ones, 500 gigabytes, 3 terabytes, we call large memory nodes. The runtime partitions, there's 6 of them. There are boundaries at 3 hours, 12 hours, 24 hours, 3 days, 7 days, and 28 days. And the 3-hour partition basically covers the whole cluster. So any job that has a runtime limit of 3 hours or less qualifies to run anywhere in the cluster. Jobs with runtime limit of greater than 3 hours but less than 12 hours can run on almost the whole cluster, just not this little bit here. But other than that, they can run anywhere. 24 hours, again, slightly more restricted, 3 days, slightly more restricted, and so on until up to 28 days. Jobs that have runtimes of greater than 7 days but less than 28 days have only got a restricted piece of the cluster that they're allowed to run on, and jobs greater than 28 days will be rejected. That's only the time dimension. There's also this by core or whole node distinction that I mentioned, and so that runs at right angles, you can imagine, to the times. By node jobs are favored in this sense because they're intrinsically harder to schedule. If you need whole nodes, then it's no good if that node has one process belonging to someone else running on it. You can't use any of the remaining cores on it. And so that's why we have the by-core, by-node distinction. A job that needs a whole node or some integer number of whole nodes and has a time limit of less than 3 hours gets access to, again, the whole cluster. A job with a 3-hour runtime limit that is requesting some smaller number of cores, or, and this is important, if it's requesting just n tasks, even if the number is 32 or 64 or 128, if it just asks for n tasks and doesn't say -- nodes equals 1, 2, 3, 4, then it has to be scheduled in the by-core 3-hour partition, which is this chunk of the cluster. And so on for the other partitions. Jobs that need whole nodes and are going to run more than a week, up to 28 days, they get access to this chunk. If you want to submit a job that's got more than a week's runtime but is just asking for some arbitrary number of cores rather than whole nodes, you've got a very restricted piece of the cluster that you're going to be scheduled on. Your job could wait a long time. There's also distinctions, as I mentioned, for memory. Memory of up to 256 gigabytes, and then the larger memory nodes and the GPU carrying nodes as well are separate partitions. Follow the same general pattern as this. How can you tell what's actually available? There's command, there's a custom script that we wrote for Cedar and Graham called partition-stats. Here you can see across the top the breakdown by wall time, the 3, 12, 24, 72, 168, and 672 hour divisions. That's 28 days, that's 7 days, that's 3 days. It'll show you the number of jobs that are waiting, the number of jobs that want whole nodes, the number of jobs that need to be scheduled in the by-core partition. It'll tell you the number of jobs that are running, It'll tell you how many nodes are idle. This is probably what you're most interested in if you want to know why your job hasn't started yet. How many idle nodes are there in each partition type? Which partition type does your job qualify for? If you asked for 4 days, then it's only qualified for one of these last 2 columns. And in the snapshot taken here, doesn't matter whether you were asking for bi-core, bi-node, GPUs, large memory, regular memory, there's just nothing available of that run length at this hour when I type partition stats. Now, if you're asking for something under 12 hours and you want large memory, you have a chance. There's a couple nodes that are idle in the whole node partition and 1 node that's idle in the bi-core partition here. The total numbers of nodes assigned to the various partitions are shown here. You may note, for example, that in the configuration when I took this snapshot, that the 3-hour and 12-hour partitions were identical. So let's return to that question. Why won't my job start? Maybe there just aren't enough slots for your job. You can try reading partition stats to decide that. Maybe they're not the right kind of slots. You're asking for a lot of time, and there's no jobs that are allowed to take, there's no machines free in a partition that's allowed to take a job of that run length, or that memory size, or that has a GPU. Or perhaps your job just hasn't gotten to the top of the priority list yet. So this is going back to what I said about the scheduling algorithm. It looks at the top priority jobs. There's a lot of jobs in our systems. I've looked, not today, but I've looked in recent days and seen 10,000 jobs involved on Cedar or Graham. Not all of those are top priority. Yours might just be waiting its turn. How can you tell if that's the case? You run squeue and look at the reason over on the far right-hand side. If it says priority, then that means you're fair ways down the waiting list in priority. If it says resources, that means you're closer to the top of the waiting list, but the machine still hasn't found the resources it needs to schedule your job just yet. A job can spend a fair period of time in the resources class, particularly if you're asking for lots of resources. Shared memory. If you're asking for 32 cores, there might be 32 cores available on the system, but if it's a shared memory task, you've just asked for 1 node and they got to be all in the same node. Actually, a smaller number would be a better example there. If you've asked for 32 CPUs for a shared memory task, you probably should ask for a whole node. If you've asked for 16 and it's a shared memory task where you've used -- CPUs per task equals 16, then it's got to go in the bi-core partition, but it's also got to get all of those 16 cores on 1 host. So that's not going to be trivially seen through partition stats or anything. You might be able to make some headway there, but that's a thing that could be happening. There's a gotcha here that I want to tell you about. You might be asking for too much memory, even though you're still down in the 128 gigabyte territory. We've got lots of 128 gigabyte nodes, right? But here's the gotcha. If you ask for 128G explicitly, you will not qualify for one of the 128 gigabyte nodes. There needs to be a little slice of memory in which the operating system resides. And if you ask for exactly 128 gig, it adds that little, Slurm adds that little slice, and you no longer qualify for those very common 128 gigabyte nodes. If you want to use all the memory on one of those nodes, you got 2 choices. One is --mem equals 128,000 meg, and because gigabyte is 1,024 megabytes, this is not exactly the same as that. The difference is enough to let you in. The other thing you can do, and it's not shown in the slide, is you can ask for like n nodes equals 1, or nodes equals 1, n tasks or CPUs per task equals 32, and --mem equals 0 will give you all the memory on that node. And it will qualify you for a 128 gigabyte node. If you actually need more than 100, if you need 128 gig, which is slightly more than 128,000 or some larger number, then you're going to have to resign yourself to waiting for one of these larger nodes. And if you ask for --memory equals 0, you will not necessarily be scheduled on one of these. So if you know you need 128 gigabytes or more, you should ask for the explicit number. If you just want all the memory on a node, you can ask for 0, or you can ask for 128,000 megabytes. So I promised I'd tell you something about priority. How is it decided where in the priority list your job sits? The model is a little bit complicated, but I think I can squeeze it into one slide. Every default project, every research group starts with basically equal rights, an equal share of the system. Now, there's an annual resource allocation competition that awards larger shares based on need and merit. But let's push that to one side for a moment and just think about a model world in which every project, every research group is equal. So we've got our new cluster, we've got a bunch of research groups on it, all with equal rights to the system. The first research group that gets their jobs running starts using up its priority on that system. The system logs how many CPU hours were used, how many CPUs times how many hours the jobs ran. And it keeps a record of that. And based on the size of that number, it assigns that research group's new jobs a lower priority. So first one on gets their jobs running, and then their priority drops, and the other people who haven't had a shot yet, their jobs get moved to the top of the priority list and are considered first for running, if they're runnable, if they're not asking for resources that aren't available. The advantage to the groups that haven't run yet does not last forever. The record of usage kept per project is decayed with an exponential half-life sort of arrangement of 1 week half-life. So a week later, it's as if you'd only run half as much stuff this week. 2 weeks later, it's as if you'd only run a quarter as much stuff this week. So there is, to a certain extent, a user-to-lose-it going on thing here, but we do try and arrange, the point of this system is to try and arrange that the people who have not had their work run recently are considered first. One of the side effects of this that surprises some people is that you get onto the new system, your research group's just got its account, and you're doing your computing on the new system for the first time, and your job's going great, and everything's wonderful, and then you pile in a whole bunch of jobs to go in production, and they wait a lot longer than your initial runs did. This is why. It's because once you actually get into production and your usage becomes a substantial fraction of the system, your priority erodes, and also there may be other new groups coming on in the meantime as well. You just have to deal with that. It does work out in the end in almost all cases. So, if you want to know more about any of these things, the place to go is docs.computecanada.ca, running jobs, the key page. There's a number of subordinate pages that you can find there from as well. If you want specifics about the options available to sbatch, and there are lots of them, if you want to read about the other options available to sbatch, you can type man sbatch, the command line. Ditto for man sq if you want to see other ways you can sort the list of the running jobs. Saccount is a command I didn't talk about, but that will let you see details about jobs that have already run, such as how much memory did they actually use. That's useful if you're running a bunch of similar jobs and you want to actually tune the amount of memory you're asking for, or tune the amount of time you're asking for. Saccount will get you that information. You can also find the same details as man will give you. You can also find at slurm.scedmd.com on their documentation site there. And of course, you can ask us for help. That's what we're here for, right? Support at ACENET.ca or support at computecanada.ca with your questions. And we'll do our best to figure out what's mystifying you and find you a solution that will keep your research moving forward. Thank you for listening.